Yield stress in structural engineering. Welcome to Blueprint to Reality, where we break down complex engineering concepts into bite-sized lessons. In this episode, we'll explain yield stress, a fundamental concept in structural engineering that plays a crucial role in designing safe and durable structures. What is yield stress? In simple terms, yield stress is the stress at which a material begins to deform permanently. Before this point, materials like steel, concrete, or wood can handle applied loads by stretching or compressing and will return to their original shape when the load is removed. However, when the applied load exceeds the material's yield stress, it starts to undergo permanent deformation, which can lead to failure if not properly accounted for. For example, imagine a metal rod. If you pull on it, it will stretch slightly but return to its original length when you release it. However, if you pull too hard, it will stretch permanently and won't return to its original shape. This permanent stretching is a sign that the material has exceeded its yield stress. Why is yield stress important in structural engineering? Yield stress is critical because it defines the limit beyond which a material cannot safely support additional loads. In structural engineering, understanding the yield stress of materials ensures that we design structures that remain functional and safe under the expected loads. If the applied stress exceeds the material's yield stress, it can lead to irreversible damage or failure, which can compromise the safety and stability of the entire structure. For example, in building design, knowing the yield stress of materials like steel beams helps engineers determine how much load the beams can carry before they start to bend permanently, which could cause the structure to collapse. How is yield stress determined? Yield stress is typically determined through a tensile test, where a material sample is subjected to increasing tension until it begins to deform permanently. This test measures the stress-strain curve of the material, which shows how it behaves as the load increases. The point at which the curve deviates from a straight line is known as the yield point, and the corresponding stress is the yield stress. In many materials, particularly metals, the yield stress is not always a single value. Some materials exhibit yielding over a range of stresses, and engineers may use the 0.2% offset method to define a specific yield stress for these materials. This method involves drawing a line parallel to the elastic portion of the stress-strain curve, offset by 0.2%, to identify the yield stress more accurately. Yield stress in different materials. Different materials have different yield stresses depending on their composition and how they were processed. For example, steel. Steel has a relatively high yield stress, which makes it ideal for use in buildings, bridges, and other large structures. The yield stress of structural steel is often around 250 MPa megapascals, but it can vary depending on the alloy and treatment. Concrete. Concrete is a brittle material, so it doesn't exhibit significant yielding. It has a high compressive strength, but is weaker in tension. Engineers often use reinforced concrete, which has steel reinforcing bars, rebar, to resist tensile stresses. Wood. The yield stress of wood is much lower compared to metals, which is why it's typically used in smaller structures like houses or furniture. However, wood is strong enough for these applications when the forces are distributed appropriately. What happens if a material exceeds its yield stress? Once a material exceeds its yield stress, it begins to deform permanently. This permanent deformation is called plastic deformation. In the case of structural elements, plastic deformation can result in 1. Bending or warping. In beams and columns, excessive load can cause permanent bending or warping. 2. Cracking or fracturing. In materials like concrete, exceeding the yield stress can cause cracks or even fractures. 3. Instability. In some cases, permanent deformation leads to structural instability, where the entire system may fail or collapse. Therefore, it is essential for engineers to design structures in such a way that no part of the structure is subjected to stresses beyond the yield point of its materials. Real-world applications of yield stress. Understanding yield stress is vital in designing elements like beams, columns, and foundations. For example, in a bridge design, engineers calculate the load distribution to ensure that the steel beams used will not exceed their yield stress under the heaviest traffic. Similarly, in high-rise buildings, knowing the yield stress of the materials used for beams, columns, and foundations ensures that the building remains safe under both static loads, like the building's own weight, and dynamic loads, like wind or earthquakes. In civil engineering, the concept of yield stress is also applied to soil mechanics when designing foundations, as the soil beneath a structure can also experience stresses that might lead to failure if they exceed its yield stress. Conclusion. In summary, yield stress is a critical factor in determining how materials behave under load. By understanding a material's yield stress, engineers can design structures that remain safe and functional, even under extreme conditions. Ensuring that materials stay within their elastic limit is essential for preventing permanent damage or failure. Thank you for tuning in to Blueprint to Reality. If you found this explanation helpful, don't forget to like, share, and subscribe for more civil engineering insights. See you in the next episode.